Around 600 BC, Greek philosopher Thales of Miletus took note of a peculiar behavior exhibited by a certain gemstone. Upon rubbing it, Thales observed that it drew in lightweight objects like feathers and bits of straw. These observations left Thales deeply fascinated and led him to conclude that this gemstone possessed some kind of lifelike quality. He gave this gemstone the name electron, the Greek word for amber, which is what the stone is still called today. Other ancient Greeks went so far as to claim that amber contained a soul, because of this strange ability, making it a highly prized possession among them. What Thales and the Greeks had actually stumbled upon, without realizing it, was the first documented instance of static electricity. Static electricity is a phenomenon where electrons either accumulate on or are stripped from the surface of an insulative material when rubbed against something, causing these materials to become positively or negatively charged and enabling them to attract objects of the opposite charge. Since Thales and his fellow Greeks had no understanding of why amber behaved this way, or how to put it to use, little came of this knowledge beyond the stone holding some intrinsic value. So how exactly did humanity move from superstitious beliefs about a gemstone to bending electricity to our will with machines? The answer lies in a systematic study of this very gemstone during the late 16th and early 17th centuries, shortly following the onset of the scientific revolution. The first major scientific revolution era breakthrough concerning electricity came from English physicist William Gilbert. Born in 1544 in Colchester, England, he earned his doctorate in medicine from Cambridge at just 25 years old. He went on to practice medicine in London and traveled extensively across Europe. In 1573, he was elected to the Royal College of Physicians, and by 1600 he had risen to its presidency. The following year, he was appointed personal physician to Queen Elizabeth I, a role he held until her death in 1603, after which he continued serving in the same capacity under the newly crowned King James I. As talented as Gilbert was in medicine, he was equally gifted as a physicist. His most notable contribution to physics was his 1600 publication De Magnete, meaning on the magnet, in which he presented a remarkable collection of discoveries about magnetic forces. Gilbert's curiosity about magnetism grew from his fascination with compass needles, and he was among the first to suggest that the Earth itself functions as a giant magnet. His discovery pertaining to electricity, however, came roughly 3 decades before De Magnete was published. He chose to investigate amber, much as Thales of Miletus had done millennia earlier, but approached it in a far more systematic way. He observed much the same thing Thales had, that gently rubbing amber with cloth or fur in a dry environment caused it to attract lightweight objects. He extended this observation to materials like glass and crystal as well. Gilbert recognized that these objects attracted things in a manner similar to magnetic objects, but since the materials he was studying were not magnetic, he drew an important distinction between the two forces. Drawing from the Greek word for amber, electron, he labeled all objects that behaved similarly to amber as electrics and called their attractive property the electric force. Gilbert thus laid the groundwork for modern electrical terminology back in the early 16th century, and his investigations didn't stop there. He also discovered that a thin film of water disrupts electric phenomena, while a thin film of oil does not. Additionally, he constructed a needle modeled after a compass, which he called a versorium. This needle was non-metallic and extremely lightweight, designed to pivot freely just as a compass needle does. When nearby objects were electrified, the needle pointed toward them, and in doing so, Gilbert also established the foundation for what we now call the electric field. At the dawn of the scientific revolution, William Gilbert took the observations of Thales of Miletus and expanded upon them enormously, coining new terms and laying the groundwork upon which future scientists would build. The first significant advance upon Gilbert's foundation came from German physicist Otto von Guericke in 1650. Von Guericke cast a ball of sulfur inside a glass mold, mounted it on an axle, and rotated it with a crank. As the sulfur ball spun, he pressed his hand against it to generate a large amount of friction and, with it, a substantial charge of static electricity. Once enough friction had been built up, the device produced sparks that illuminated the dim room around it. Von Guericke was the first person to generate both sparks and light from electricity. Decades later, English scientist Francis Hauksbee improved upon von Guericke's apparatus. In 1709, he built a hollow glass sphere, evacuated the air from within it using a vacuum crank, mounted it on an axle, rotated it, and pressed his hand against it. He observed that the glass globe filled with a light bright enough to read by. 20 years after Hauksbee, an English scientist named John Wood discovered that these static charges were capable of far more than producing light when rubbed. Wood recognized that these charges could be carried along metal pieces, hinting at the concept of conduction. This idea was taken considerably further just 3 years later by an English electrician who would fundamentally reshape the understanding of electric charge and how it could be applied, moving the field from simple tricks to long-distance conduction. Stephen Gray was born in 1666 in Canterbury, England. His father earned a living dyeing cloth, and Stephen carried on the family trade while pursuing science as a hobby. His interests spanned many disciplines, from astronomy and chemistry to biology and physics. He even fashioned his own microscope, using a water droplet as a lens, and ground his own telescope lenses, which he used to observe eclipses, sunspots, and the moons of Jupiter. He had dabbled in electrostatics throughout much of his life, but made little headway. Then in 1729, at the remarkably seasoned age of 63, he achieved a significant breakthrough. Gray had acquired a flint glass tube 3 feet long and 1 inch in diameter. He plugged both ends with corks to keep out dust and used it to conduct experiments in which he rubbed the tube to test electric forces. One particular thing he noticed during these experiments was that after rubbing the tube, the objects attracted to it were equally attracted to the corks at its ends. In that moment, he recognized his breakthrough. The electric charge generated by rubbing the tube had transferred to the corks, meaning electric charge could be passed from one object to another. Seized by excitement, Gray tested everything he could find: silver coins, twine, brick, even a head of cabbage. All produced the same result. When connected to the tube, each one became electrified. Immediately following this discovery, one question consumed Gray's mind: how far could this electric transfer travel? He set out to find the answer, beginning in his own room, where he successfully transferred electric charge from the tube to an ivory ball across 18 feet of sticks and canes. Needing more space, he visited friends John Godfrey and Granville Wheeler, who had considerably more land to work with. Together, they managed to transmit electricity 886 feet through a thread of twine. A monumental achievement. But in conducting this experiment, the three of them also made 2 additional significant discoveries at the same time. In order to carry electricity through the twine, they had to suspend it in the air. On Godfrey's estate, they did this using additional lengths of twine strung vertically and nailed to the ceiling. When they did, they found that no electric charge reached the ivory ball at the far end, and Gray was baffled as to why. He brought the problem to Wheeler, who suggested that the electricity was indeed transferring, but escaping through the nails in the ceiling rather than traveling to the ball. To address this, Gray switched the suspension lines from twine to silk, reasoning that silk's greater thinness meant it would not carry electricity. The experiment worked. The charge successfully reached the ball. During repeated trials, the silk threads eventually snapped under the weight of the twine. They replaced them with brass wire of the same thinness as the silk, assuming the charge would not escape through something so thin. It did, however. And this led Gray to understand that it was not the thickness of the material, but the material itself, that determined whether electricity would transfer. This realization led Gray to build upon Gilbert's theory, ultimately proposing that the terms electrics and non-electrics be replaced with conductors and insulators. Metals, for instance, conduct electricity, while silk serves as an effective insulator. By 1730, a century and a half after Gilbert's original theories, humanity had advanced from basic electrostatics to conducting electricity across considerable distances. Just 3 years after Gray, Godfrey, and Wheeler's landmark discoveries, French chemist Charles Franz de Cisternay du Fay was building on their work when he noticed something critical. Some charged objects attracted one another, while others pushed each other away. This led him to propose that there were two distinct types of electrical charge, which he labeled vitreous and resinous. He also found that any object, solid or liquid, could be electrified if first placed on glass stands, a finding that contradicted Gilbert's claim that water dissipates electric charge. Dufay even observed that in certain cases, moisture actually aided the passage of current. He also noted that objects most easily electrified by friction were the poorest conductors, or conversely, the best insulators. At this stage in history, it was understood not only that electric charge could be produced through friction, but that it could be transmitted through wires across long distances. It was also known that two types of electric charge existed, and that like charges repelled while opposite charges attracted. The next logical step was finding a way to store this charge for convenient use, and this was achieved independently by two men, German scientist and cleric Ewald Georg von Kleist in October 1745, and Dutch professor and physician Peter van Musschenbroek in January 1746. Von Kleist's invention came about by accident. He had set up a medicine bottle filled with fluid and sealed with a cork, through which he hammered a nail so that it passed fully through and touched the liquid inside. He had also recently built a machine capable of conducting electricity and connected it to this arrangement. Upon doing so, he noticed a pencil of fire surrounding the nail that remained as he walked 60 paces around his room, holding the bottle. After a short while, he touched the nail and received a powerful shock that stunned his hand and arm all the way up to his shoulder. Filled with amazement, von Kleist wrote to several colleagues describing the device, claiming the liquid inside had stored electrical energy over time. None of them, however, were able to successfully replicate it. A few months later, van Musschenbroek announced his own version of a very similar device. His was presented to the Academy of Sciences in Paris in April and demonstrated so clearly that it was easily replicated by others. Von Kleist had arrived at the idea first, but van Musschenbroek was the one who made it reproducible. The device was eventually named the Leyden jar, after the University of Leiden, where van Musschenbroek had developed it, and it stands as the first ever capacitor. By the 1750s, electricity had become one of the most popular subjects in science across the entire world. Everyone wanted to contribute to the field in some way, and in their search for new avenues of experimentation, some turned their attention to a new frontier: the sky. Leading this charge was American polymath Benjamin Franklin. Franklin's interest in electricity was sparked in the 1740s after attending demonstrations on static electricity by a lecturer named Archibald Spencer. After a few years of conducting his own experiments, Franklin put forward a new idea about the nature of electricity. He pushed back against Dufay's concept of vitreous and resinous electricity, proposing instead that the two were one and the same. Drawing on the popular theory of electrical fluid, he likened electricity to a fluid and argued that the two apparent types were actually the same fluid behaving differently under different pressures. He suggested replacing the terms vitreous and resinous with positive and negative, names that endured and are still used today. In 1752, Franklin undertook his most daring and most celebrated experiment, proving that lightning was a form of electricity by flying a kite through a storm. He had proposed the idea earlier that year, though with a general conductor rather than a kite. In May, French physicist Thomas François Dalibard realized the concept using a 12-meter iron rod grounded by wine bottles instead. Rather than waiting for a lightning strike, Dalibard extracted electric charge directly from a cloud, demonstrating that atmospheric electricity and friction-generated electricity were one and the same, marking the first ever lightning rod experiment. The following month, Franklin carried out his own iconic kite experiment. Contrary to popular imagination, he was not simply standing in a field waiting to be struck. The experiment was far safer than that. He took precautions such as standing on an insulator and sheltering himself under a dry surface. In a letter to England, Franklin described the experiment and provided instructions for replicating it. He noted that once rain had soaked the kite twine, making it a good conductor, electric fire streamed from the key as a knuckle approached it. And from this, a Leyden jar could be charged and all the usual electric experiments performed, fully demonstrating that lightning and electricity are one and the same. Franklin's work with lightning ultimately led him to invent the lightning rod, specifically one with a pointed tip, which he found discharged electricity silently and at a far greater distance than a rod with a smooth end. Following Franklin's contributions, electricity was understood as something present virtually everywhere, a force that could be generated through friction and carried across long distances for brief periods. The next challenge was extending those brief periods into sustained ones, and that breakthrough would not arrive until the turn of the 19th century. The two most influential figures in electricity directly following Franklin were Italian physicists Luigi Galvani and Alessandro Volta. It was, in fact, a scientific disagreement between them that led to an invention that altered the course of the world. Galvani, in addition to being a physicist, was a prominent physician with a deep interest in animal anatomy. He experimented frequently on animals and was particularly fascinated by frogs. His pivotal experiment came in 1786, when he touched a frog with a pair of scissors during an electrical storm and triggered a muscular contraction shortly after. Records from his laboratory describe someone touching the lumbar nerve of a skinned frog with a scalpel while an electrical machine was running, causing the frog's legs to kick. From these observations, Galvani developed his theory of animal electricity, the idea that living tissue itself produces electricity, and that metals merely conduct it through friction. Upon learning of this theory, Volta disagreed sharply. He was convinced that the electrical stimulation was a purely physical phenomenon and had nothing to do with animal tissue, and he set out to prove it. Through the 1790s, Volta conducted experiments with various combinations of metals and electrolytes, and by 1800, he had built a device capable of storing electricity. His invention, called the wet pile, was made of alternating discs of zinc and silver separated by layers of paper, and cloth soaked in a solution of salt or sodium hydroxide. This device was unlike anything before it. It could sustain electric circuits for extended periods, finally bridging the gap between short bursts of current and a continuous, lasting supply. Volta's pile served two key purposes. First, it provided evidence that Galvani's frogs were merely conductors of electricity rather than its source, since the pile produced electricity using only metals and electrolytes. Second, and far more consequentially, it was the world's first battery, arguably the more transformative of the two outcomes. The pile elevated electricity from a laboratory curiosity to an actual power source, one that would go on to drive the development of technology for generations to come. There are many directions one could take from here in tracing the development of electricity, but I'll keep things relatively concise, as this video has already covered considerable ground. If I were to highlight two more pivotal contributions, they would be Willow Rosted's discovery that electricity and magnetism are part of the same electromagnetic force, and Faraday's discovery that a changing magnetic field induces an electric current, the insight that gave rise to the first generators. I've covered Rosted's discovery in a separate video, which I'll link here for anyone interested. And I would feel remiss making a video on electricity without dedicating at least a little time to Michael Faraday. In August of 1831, Faraday wrapped two coils of wire around opposite sides of an iron ring. The wires were insulated with cotton, so they had no direct contact with the ring. One coil was connected to a battery, the other to a galvanometer, a device that detects electric current by generating a magnetic field and deflecting a needle when current flows through it. When Faraday switched on the battery to send current through the first coil, he noticed a deflection in the galvanometer. However, the deflection was brief and only occurred at the moment he switched the circuit on or off, not while the current was steadily flowing in either direction. From this, Faraday concluded that it was the change in the magnetic field, caused by switching the current on or off, that induced an electric current in the second coil. Faraday's induction ring is recognized as the first electric transformer, and he was far from finished. That September, he repeated a version of the experiment, but this time attached the wires to a copper disc in a sliding contact arrangement, rather than wrapping them around it. He continuously spun the copper disc between the poles of a horseshoe magnet, and the setup produced a steady direct current, widely considered the first generator ever built. Limiting Faraday's legacy to just these two experiments is a considerable understatement of his influence, but for the purposes of this story, they are the most relevant. Every scientist mentioned throughout this video built upon the discoveries of those who came before them, and each of their contributions cannot be overstated. Understanding electricity required the efforts of many people across countless experiments, and the work continued well beyond Faraday into the modern era, carried forward by pioneers including Maxwell, Joule, Kelvin, Hertz, Tesla, Westinghouse, and many others. Perhaps a future video can explore their contributions, but for now, this is where the story ends. In the span of roughly 260 years between 1570 and 1830, electricity transformed from little more than a scientific enigma into a force that could be harnessed at will to produce powerful currents that would ultimately come to power all of modern society. If you enjoyed this video, please consider liking and subscribing. Click here if you'd like to explore more of the scientific progress made during this era. Thank you for watching, and I'll see you in the next one.